Hi everyone. So last time we talked about, I introduced the queuing theory, right? So we talked about how the basic queuing process works, and we also discussed fundamental concepts of queuing theories and some necessary basic terminologies as well. Okay, so many of queuing models assume that all the inter-arrival times and the service times are identically and independently distributed, simply IID, right? And such models conventionally are labeled using Kendall's notation. And in the Kendall's notation, the first character specifies the distribution of inter-arrival times. So it shows the nature of the arrival process. And the second characteristic specifies the nature of the service times. And the third one is the number of parallel servers. And the fourth one is the maximum allowable number of customers in the entire system, including those in service as well. So the fourth character specifies the system capacity, basically. And this number can be infinite number or finite numbers. And it is omitted if infinity. Okay? And the fifth character gives the size of entire source population from which customers are drawn. Okay? And it may be also finite or infinite, and it is omitted if it's infinity. Okay? And the last characteristics shows the queue discipline or service disciplines. The default value is first come, first service. So it can be also omitted if it's first come, first service. Okay, earlier we talked about a burst process. That is a continuous time stochastic process, right? Which models the size of population. So the burst process, a burst increases the system state by 1. And here, the variable lambda j, lambda 0, lambda 1, lambda 2, and so on, this lambda j's. Okay. So these lambdas, they are called burst rate in state J. What happened? Lambda J. Do you know what happened today? Okay, let me just do this. Okay. And this lambda J, in most queuing systems, this burst is simply indicating an arrival of the customers. Okay? And the depth in the burst process decreases the system state by 1, always. Right? See here, it decreased the number of state of system by 1 all the time. And the variable mu here. So I just say, what happened here? Mu j, I don't know why. So mu j indicates the death rate in each state j. Okay? In most queuing system, death is simply indicating a service completion. Okay? And most queuing system with exponential into arrival times and exponential service times may be modeled as burst-as process. Okay? And for a burst-as process, steady-state distribution can be obtained by solving these streamlined flow balance equations. And we practiced this a couple times earlier. Okay? And earlier we also talked about Litter's law. And this Litter's law applies to any queuing system having a steady-state probability distribution. And it relates the mean queue length to the arrival rate and mean response time as well. So with a small modification here, we can also say that LQ instead of L and WQ instead of W. So LQ is the average number of customers waiting in line, okay, waiting in the queuing line. That doesn't include the customers who is being currently served, okay. And WQ is the average waiting time spent in the waiting line, okay. Also here, just like L equals lambda bar W, we can use LQ equals lambda bar times WQ. Okay? So all of these are key measures of performance for the queuing system. Or actually, here, we're talking about LQ and WQ. And here's the corresponding formula, how you can get WQ and LQ as well. Okay. Okay, so now let's talk about MM1 queuing system. So this is a single server case, right? You remember this third characteristic represents the number of servers, right? And here, the first M's indicating the interarrival times and service times. Both follows the exponential distribution, right? So that both of them has Markovian property or memory list property. So we have M1, okay? So, like I said, MMO model has a Poisson input and exponential service times. And it is assumed that the queue has infinity, right? Infinite capacity. And here, in this case, we assume that lambda is less than mu, so that the queue length does not tend to increase indefinitely. Okay? So here, if we define, let's say, low, how come? So low is equal to, I don't know why it happened today. Low is equal to lambda over mu. Then we can call this rho as the traffic intensity. This is the traffic intensity of the queuing system. So here, we're saying mu is greater than lambda. So this implies that low is less than 1. Is that correct? Right? So let's draw a rate diagram for the MM1 model. So starting from 0, 1, 2, 3, 4, and so on. What happened today? They act very weird today. Okay, let me use different program. I don't know why it doesn't work quite well today. So let me use the smartboard instead of PowerPoint slide. So I'm going to draw the MM1 model. So we are drawing MM1 model. So starting from stage 0, 1, 2, 3, 4, and so on. Okay. In MM1 model, the arrival, mean arrival rate will be lambda all the way. Okay. And the service rate is going to be also mu all the time. Okay. So simply saying that, we know that in MM1 model, lambda n is always same as lambda for every state, right? Starting from 0, 1, 2, and so on. Likewise, service rate, mu n, is always equal to mu for each state, 1, 2, 3, and so on. Okay. Now, what you can see here is, from this diagram, we can say that this is the burst test process, obviously, right? Because the state of the system increased by 1 all the time and decreased by 1. And we are also assuming that the arrival of the customers independent from the service of the customer. So obviously this is the burst test process. So we should be able to use the streamlined version of the balance equation, right? So let's use that. So what is that? Do you remember? It's going to be 1 over pi 0 equals 1 plus lambda over mu, right? Plus lambda over mu square, lambda over mu cube, lambda over mu to the fourth power, and so on. Is that right? So this is a geometric series. So what is this? That's going to be 1 over 1 minus lambda over mu. So what do we have here? pi 0 is equal to 1 minus lambda over mu. Okay? Once you get pi 0, the other pi's can be easily obtained by, for example, pi 1 is this times pi 0, right? So that's going to be lambda over mu times pi 0, 1 minus lambda over mu. Is that right? How about pi 2? Pi 2 would be this next term times pi 0. And then pi 3 would be this times pi 0. Pi 4 would be this times pi 0. So I can say, let's say here, pi I would be same as i's power up here. Okay? So using this formula, you should be able to determine steady state probability distribution. Does that make sense? Right? Okay, then let me ask you, what is the probability that no customers are in the system so that the server is idle in this MM1? Keep in mind that there is only one server. What is the probability that the server is idle? Pi 0, right? So I'd say pi 0 is the probability that the server is idle, which is 1 minus lambda over mu in the MM1 system. Then what is the probability that the server is busy? 1 minus pi 0, right? Simple. So I just say 1 minus pi 0, which is lambda over mu. This is the probability that the server is busy. Is that right? So I just say this is the utilization of the server. Does that make sense? So this is the utilization of the server, which is previously I defined earlier here. Okay. I mentioned law is lambda over mu, right? So going back to here, this is same as law, right? Which is less than 1. So obviously, in the MM1 system, server utilization is less than 1. That makes sense, right? Okay, so now let's move on to the next screen. Okay, next, the average number of customers in the system for MM1 system. And this number including any customers being served. That is represented by capital L, right? And that is law over 1 minus law. I believe any operation research book or stochastic process textbook, they drive this formula. So if you are interested in, I want you to refer to those textbooks or any other reading materials. Okay? So MM1 model, L is computed by lambda over mu minus lambda. And for the MM1 model, Litter's formula also imply that W can be obtained by 1 minus mu minus 1 over mu minus lambda. Okay? Also, WQ is this, and LQ is this. But keep in mind that all of these formula works only for MM1 queue. Okay? So anyhow, given any one of these quantities, L, W, LQ, WQs, we can compute the others. And generally, I would say the L is the easiest one to compute first. But you can go with others first if you want. Okay? Okay, now let's take an example problem for MM1 queuing model. So in this example, an average of 24 trucks per 8-hour day arrive to be unloaded and or loaded, which requires an average of 15 minutes. And the loading dock can handle only a single truck at a time. We assume that the arrival process is Poisson and that the service times have exponential distribution. So this loading dock can be modeled as an MM1 queue. Okay, that's why I specify up here MM1 model example. Okay, so let's use the smart book, smart notepad. So what is the arrival rate? What is the arrival rate? Lambda? (24/8), which is 3 per hour. Is that right? Okay. And then what about the service rate? Mu. Keep in mind that we're going to use the same unit. You can go either with minutes or hour, but because we already use hour, let's stick to the hour as the service time instead of 15 minutes. Okay? So how many hours are 15 minutes? 1/4, right? 1/4 hour is the service minute, right? Service hour. So service rate would be 4 per hour. Is that right? So simply it's going to be 0, 1, 2, 3, and so on. That's going to be 3, 3, 3, 3, 4, 4, 4, 4. Right? Very simple rate diagram because it's MM1. Okay, then what is the utilization of the server? You remember? Lambda over mu, which is low. That is the utilization of the server. That is 3/4. 0.75, right? What is the average number of trucks in the entire system here? Which is L. What is that? Remember, low over or minus low. So 0.75, 0.25, which is 3, right? What is the average time in the system per truck? Which is W? There's L over lambda. Lambda bar. Actually, in this case, lambda bar is same as lambda, right? Because this is the infinite system. Always the arrival rate is equal to 3. So lambda bar is also same as lambda, right? So what is this? 3/3 per hour, which is 1 hour. Very simple. Is that right? Likewise, you can also determine WQ, LQ as well. Either you can use the formula or you can count on it. Either is fine. So can you do that, right? Okay, so now let's get back to the slide. Now let's talk about MMC. MMC model also has a Poisson input and exponential service times. And so main difference from MM1 model is that this time this is the multiple server case, right? So C here is greater than 1. So we have multiple server in the MMC model. And of course, the capacity of the queuing system is infinity, right? And the rate diagram for MMC queuing model is just like this. All right? So from here, lambda n is equal to lambda, right? Always for n equals 0. I don't know why it happened today. 2, 3, and so on. Okay. What about mu? That's going to be, let's say, n times mu. For n is equal to 1, 2. Okay. I gotta use SmartPad because I don't know what happened today. So PowerPoint slide doesn't cooperate with me. Okay, so let me redraw the MMC rate diagram here. 0, 1, 2, and then let's say C minus 1, C plus 1, okay, and so on. As always, lambda, the arrival rate is all the time the same, right? But the service rate is different, right? It depends how many servers are there. And then here, let's say C mu, C minus 1 mu, C mu, C plus 1 mu, and so on, right? So lambda is all the time same for every state, 0, 1, 2, and so on. But mu is different. It's going to be n times mu for n is equal to 1, 2, 3, and so on, until n equals c, okay? And for n is greater than or equal to c, what happened? That's going to be same as c mu. Is that right? So this is the main difference between the MM1 model and MMC model. Of course, here, if you look at this carefully, only this portion, all the servers busy. Is that correct? Right? Only this portion of the system, queuing system, all of the servers are busy. Okay, all the way. Okay, now let's consider MM2 model instead of MMC. So let's use MM2. What happened? So you have transition diagram, rate diagram, like this. So we have lambda all the time. And then here we have mu and 2 mu. If there are 2 customers and both servers will be busy, so you need to multiply by 2, right? And then although there are 3 customers here, since you have only 2 servers available, the service rate would be 2 mu since then. Is that right? Now, again, using the streamlined version of balance equation, we can determine the steady-state probability distribution, which is lambda over mu, right, plus lambda over mu times lambda over 2 mu, right, plus lambda over mu, lambda over 2 mu square, lambda over mu, lambda over 2 mu cube, and so on. Is that right? So what I'm going to do is, from here, I'm going to take out lambda over mu. So instead of having lambda over mu, I'm going to have 1 inside the parenthesis. And then I'm going to have lambda over 2 mu, right? Plus lambda over 2 mu square, lambda over 2 mu cube, and so on. Is that correct? So obviously, these are the geometric series, okay, which converges to 1 over 1 minus lambda over 2 mu. Of course, if lambda over 2 mu is less than 1, okay? So from here, we can say that pi 0 is equal to 1 plus lambda over mu, I'm sorry, there is pi 1 over pi 0. So 1 over pi 0 is equal to 1 over 1 minus lambda over 2 mu. Is that right? And, you know, you can do this for MM2, MM3, because we already done for MM2, and MM4, MM5, and so on. Eventually, you should be able to generalize the formula, okay? which is like this. Okay? So this is the generalized formula for MMC model. Okay? So in this case, if the arrival rate lambda is less than the combined rate, which is C mu, at which the servers can work, then the system will have a steady state distribution, which is given by this. Okay? So again, in this case, we define lambda over C mu is equal to rho. And again, rho is the what we call traffic intensity of this queuing system, MMC system. Then, by assuming this, lambda is less than C mu, we can say that rho is less than 1, which is down here. Okay? And in this case, the average length of queue, which is LQ, can be obtained by using this. Once the LQ is computed, then we can also compute using Litter's formula, WQ and WR, and so on. Okay? Any questions so far? Okay, then now let's compare two queuing systems. One is separate queue per each server. Here we have two servers. Okay. In this queuing system, right? We have two servers. So we have separate queue per each server. So this is actually two MM1 model. Is that right? And the second case is, let's say, pooled server case. So this is a single So this is the, I don't know why. It's very sensitive. So this is the single MM2. Is that right? Because we have two servers. But the main difference is we have only one queuing line. Okay? So I believe the first case is something like McDonald's or Walmart, Target store, something, right? So you're going to have as many queuing lines as the number of servers, right? But the second case, this case, is more likely the bank. If you go into the bank, regardless how many cashiers there, how many clerks there is always have only one queuing line, right? So let's compare these two queuing systems. So in this case, in the first case, 2 MM1, the arrival rate is 4 per hour, okay? And the service rate is 5 per hour. And the second case, the pooled server case, the arrival rate is 8 per hour. And the same service rate, which is 5 per hour. So let's use the smart board. So I'm going to use the 2 MM1 case. Okay, so we have in that case, what is the average waiting time? WQ. What is the waiting time? That's the lambda over mu times mu minus lambda, right? So what is this? 4 over 5 times 5 minus 4. What is this? 4 over 5. That is 0.8, right? So that's going to be 0.8 hour. How many minutes are 0.8 hour? You need to multiply by 60, right? Then how many minutes is that? 48 minutes, right? So I would say for 2 MM1 case, the average waiting time is 48 minutes. Let's see what happened to the single MM2 here. Okay, we're going to get WQ value. That's what I'm going to do. Okay. So rather than maintaining a separate queue for each server, in this case, customers enter a common queue, only one queue, right? So in this case, what is the law? That is lambda over 2 mu. What is this? 8 per hour times 2 times 5 per hour, which is 0.8. Obviously, that is less than 1, which implies that the steady state exists for this queue. Okay? So in that case, you should be able to get pi 0. Okay? Using the formula we just drove, right? Earlier. So using this formula, you should be able to get pi 0. Right? Just ago, we talked about how we can determine steady state probability distribution for MM2 model, right? So we're going to grab this formula to determine the pi 0 value. So I believe I got this value. Okay, so in my previous calculation, I've got pi 0 is 0.111111, okay? And pi 1 is 0.177777. Okay? So in that case, what is the probability that both servers busy? Both servers busy. What is this probability? We are considering 2 server queuing model. So it's going to be 1 minus pi 0 minus pi 1. Is that right? That is the probability that both servers busy. So 1 minus 0.111111 minus 0.17777. So that's going to be 0.7111111, something like that. Okay? Now we should be able to get LQ. That's going to be 2.8 4444. I just used the formula. Okay. Then from the Litter's law, WQ is LQ divided by lambda. That's going to be 0.35156 hour. That's going to be about 21 minutes, approximately 21 minutes. Okay? So let's go back to this. So previously, for this case, for the first case, the RQ, average waiting time was 48 minutes, right? But right now, is that 21 minutes, right? 21 minutes. So which one is better in this case? Second one is better, right? So by pulling the servers, the average waiting time per customer is reduced approximately more than 50%. That's amazing, right? For this special case, okay? Does that make sense to everyone? Okay. Okay, now let's talk about MM1NQ. So this is a finite Q variation of the MM1 queuing model. Again, the interarrival times and service times both have exponential distribution with parameters lambda and mu, respectively. And we have only one server, single server. But the capacity of the queuing system is finite, which is equal to n up here. And this number n includes the customer currently being served. Okay, keep in mind that this number n includes the number of customers currently being served. And of course, in this case, the arriving customers buck when the queue is full. Okay, keep in mind that. So in other words, we analyze MM1N queuing model is identical to the MM1 queuing model, except for the fact that when there are n customers already presented, then all the arrivals are turned away, right? And they are forever lost to the system. Keep in mind that. Okay? And the transition diagram for MM1N model is like this. See, it's a very simple model. The arrival rate is always lambda. Service rate is always mu. And there is only the m+1 states, starting from 0 to n. Okay? And the steady state distribution can be obtained by using the same streamlined version of balance equation, because obviously we are dealing with burst-test process, right? Of course, this is the finite geometric series with sum equal to 1 minus log to the m+1th power over 1 minus log. Okay? So that's why we have pi 0 is equal to this. Once you get pi 0, determining pi j's, other pi values, a piece of k. Just use the formula. Okay. And just to let you know, in this case, the low value is not restricted to be less than 1 for the steady state to exist. Rather, I would say low is not equal to 1. Okay? And keep in mind that the customer arrival rate is 0 when there are n customers in the system already for the MM1N model. Okay? So we can determine average number of customers in the system like this. And also using the Ritter's law, we can determine average time in the system per customer. So also keep in mind that these formulas works for MM1N Q only. Okay? Okay, now let's take an example for the MM1N model. Okay, so in this example, an average of 40 cars per hour are tempted to use the drive-in window at the taco bar restaurant. And if 5 cars, including the one at the window, in line, then no cars will join the line. Okay. And it takes an average of 4 minutes to serve each car, with time having exponential distribution. Okay, now let's use the smart pad to draw this transition diagram, rate diagram. So if I define the state of system as the number of cars arrived at the taco bar, then we have 0, 1, 2, 3, 4, and 5, right? And we have our arrival rate of the customers and the service rate. And what is the lambda? What is the lambda? Lambda is 40, right? 40 cars per hour. So we have 40s. But there will be no arrivals if there are already 5 cars, including the one being served in the window, right? So the arrival rate here would be 0, right? So it will not be included in our transition diagram. What about the service rate then? Service time, average service time is 4 minutes. So how many 4 minutes are there within 60 minutes? 15, right? So the service rate should be, so it should be 15 per hour. So we have 15 like this. Excuse me. So obviously this is MM1, what? MM15, right? This is MM15 model using Kendall's notation. Is that easy, right? Because this third characteristic shows the number of servers. Fourth one is the system capacity. So here, the utilization of the server is lambda over mu, which is 40 over 15. Eight over 3. And how we can get steady state probability distribution for this case. Using the formula, it can be obtained by 8 over 3 to the 6th power divided by 1 minus 8 over 3. That's going to be 215, okay, from my previous computation. So this indicates that pi 0 is 1 over 215, okay? So once you get pi 0, pi 1 would be log times pi 0, pi 2 is log square pi 0, pi 3 would be log cube pi 0, pi 4 is log to the 4th power times pi 0, pi 5 would be log to the 5th power times pi 0. So you should be able to get all of these pi values very easy. And of course, you can determine error, right? Number of cars per hour served. And no, this is the number of cars, right? In the entire system, in the Taco Bell. Then, what about the number of cars per hour served? What is the number of cars per hour served? How do you answer that? That's the lambda bar. Whoever arrived, they will be served, right? So that's going to be lambda bar. Of course, we can get the average waiting time, W, and also we can get WQ, RQ, right? And so on. So building up this transition diagram is the key thing. Once you get it, then you should be able to answer a lot of questions, okay? So developing the transition diagram is the most important thing, of course. Okay, now let's talk about MM1 and N model. Of course, this is the single server queue. Because there is one here. Okay, I don't know open here today. So it doesn't allow me to use the pen today. So, okay, so this is the single server queuing model. The capacity of this queuing system is finite. How do you know that? The first characteristic is N, right? And the arrival service process, so memory release. So the service times have exponential distribution with mean rate of 1 over mu. And departure, so each customer in this case, after being served, they return, okay? They return to the source population here. So once they get served, they return. Probably it's better. I'm going to delete this. Okay, that's better. So here, this indicates single server, right? And this fourth characteristic indicates the capacity of the queuing system is N. And this number N, including the customers currently being served, right? And in this case, each customer, after being served, they return to the source population. For a length of time, having the exponential distribution with mean of 1 over lambda, okay? So in this case, the source population is also restricted. to the number of n, because the fifth characteristic is equal to n. Okay? So do you remember one day we talked about the light bulb repairman problem, for example. So in that case, repairman take care of only limited number of light bulbs, right? For example, three light bulbs or 5 light bulbs. Then those numbers, 3 or 5, will be the total number of population in this case. Okay? So in each state, do you remember, we're going to count how many light bulbs are in good condition, how many are not in good condition, right? So that's the good example of this queuing system, MM, 1, and N, Q. Just keep in mind that. Excuse me. Okay, so this is the transition diagram for MM1 and N model. And simply this screen shows you the formula for determining the steady state distribution, okay, probability distribution. Okay, then let's take an example. We have 2 examples. Okay, in this example, a coin-operated dry cleaning store has 4 machines. Okay, and so these machines break down with a mean rate of 1 per day. And the repair person can fix the machine with a mean rate of 2 machines per day. Okay? And currently there are 2 repair persons on duty. And the manager has the option of hiring what he called super repair person instead of having the 2 repair person. And the super repair person could fix the machine at the rate of 4 machines per day. Okay? So twice as fast. And the manager wants to maximize the probability that all 4 machines are running. So what is the probability? Probability that all 4 machines are running. Is that pi 0, right? If we are saying that the state of the system is the number of machines in good condition, then pi 0 would be the probability that all 4 machines are running. Then he's in dilemma whether he should hire the super repair person, or he should just go with the 2 repair person that he currently have. So let's see what he can suggest. So what is the current case? In the current scenario, that has 2 servers, right? So we can draw the transition diagram. 3 and 4, because they are operating only 4 machines, right? So for each state, here if I define the state of system is the number of good machines. So, no, let's say number of broken down machine. Okay, probably that'll be easier, maybe. So we are defining the state of system is the number of broken down machine. That is the state of system. So in state number 0, how many machines are broken down? No. How many machines are broken down here? 0. Right? So we're going to have all of these machines are in good condition. Is that right? In state number 1, 3 of them are in good condition and only 1 is broken down. Likewise here, we have 2 good, 2 broken down, 1 good, 3 broken down. And we have all 4 machines are broken down in state number 4. Is that right? And then what is this rate? That's going to be the failure rate, actually, right? So 1 broken down, then later on, we have only 3 good machines, right? So this is going to be the failure rate. So what is this? Lambda times 4, right? Because out of 4 good machines has the same failure rate of lambda. So you need to multiply by 4. Here we have 3 good machines in state number 1. So you have 3 times lambda as the failure rate. 2 times lambda and then lambda. Is that right? Okay, then what about this service rate on the other hand? Okay. Here in this state, 4 machines are not in good condition. However, you have only 2 servers, right? So in that case, both servers should be busy. And each server has a service rate of mu, right? So you need to multiply by 2. Although there are 4 machines broken down, since only 2 servers are available. Here, 2 times mu, 2 times mu, right? But here, since there is only 1 machine broken down, the service rate would be 1 mu. Does that make sense? So in that case, you should be able to get the pi 0 value. There is the probability that all 4 machines are running, right? Likewise, for the second case, which is one super repair person case, right? So what is this? 0, 1, 2, 3, 4. And there is a arrival rate, right? Which is 4 lambda, 3 lambda, 2 lambda, 1 lambda, right? This time, what is the service rate? That's going to be mu all the time. Right? So by the way, what is this? In Kendall's notation, what is this? It's going to be M2, right? Because there are 2 servers, right? And then, sorry. So M2, 4, 4. Is that right? How about this down here? What is this? M 1, right? 4, 4. Is that right? Of course, in this case, we have different mu value. Up here, what is the value of mu? It is 2, right? But down here, we have mu value becomes 4, okay? Unless otherwise, of course, the lambdas are the same as before. And you should be able to get pi 0 value in this case. And then compare these two, pi 0, right? And then you're going to go with whichever provide the higher value of pi 0. That will be the better option for the manager. Does that make sense? Right? Okay. I didn't get you the exact value, but it should be easy for you to determine. Okay. Okay, so let's consider another example too. Okay, so this example, NMSU Police Department has 5 patrol cars. A patrol car breaks down and requires service once every 30 days. And the department has 2 mechanics, each of whom takes an average of 3 days to repair a car. And time between breaks down and repair times are both have exponential distribution. So this is very similar to the previous case, right? Okay. Obviously, this is the 2-server case, right? So looks like it's MM2. And what about the system capacity? It's 5, right? And since they are taking care of only 5 petrol cars, the entire source population is also going to be equal to 5, okay? So it's going to be MM255 model. So let's draw the transition diagram for this. 0, 1, 2, 3, 4, and 5. Of course, the state of system will be the number of cars broken down. Okay? Then we have our failure rate and repair rate down here. Okay? So what is the failure rate? By the way, what is the lambda? What is the failure rate? It's 30 days, right? So the failure rate would be 1 over 30 per day. Is that right? What about the service rate then? It takes 3 days to repair, right? So 1 over 3 per day. That's going to be the service rate. So up here, the failure rate would be lambda times 5, right? 4 lambda, 3 lambda, 2 lambda, 1 lambda. Down here, 2 mu, 2 mu, 2 mu, 2 mu, and 1 mu. Because there is only 2 repair facilities available. Very easy, right? Of course, you should be able to get pi zeros simply using the streamlined balance equation, maybe as 1 plus 5 lambda over mu, 5 lambda, 4 lambda over mu 2 mu plus 5 lambda, 4 lambda, 3 lambda over mu 2 mu square, and then 5 lambda 4 lambda 3 lambda 2 lambda, right? Mu times 2 mu cube plus 5 lambda 4 lambda 3 lambda 2 lambda lambda mu 2 mu to the fourth power. If you do this, you should be able to get pi 0, right? Then what is the question? Okay, what is the average number of petrol cars in good condition? So, what is this? How do you answer this? That's going to be R, right? What is the average downtime for a car that needs repair? How do you answer this? What is the downtime for a car that needs repair? That is a waiting time, right? So it's just W, right? So once you get R, you know lambda bar, so you should be able to get W as well. Okay, so this is all for today. So we talked about a lot of different things for today because today is the last class, and I tried to give you some good information regarding the queuing theories. But like I said earlier, if you are interested in the queuing theory, then I highly recommend you to take queuing system. I believe it's I don't know, I forgot. Is it IE 522 or? I'm sorry, I forgot the course number. But our department offering the queuing system as a separate course. So I highly recommend you to take that class. Queuing system is very interesting topic. Of course, it does require pretty good amount of math and calculations, but it has a really good application, real-world applications. A lot of people, researchers, has been using queuing theories, okay, for many different application areas. So I highly recommend you to think about taking those classes. I really would like to thank everybody. Hopefully everyone has a good time and have a productive semester with IE 515 class, the stochastic process modeling class. This is very first time for me to teach this in the graduate level. So I believe I made a couple of mistakes, maybe, during the regular class, but I tried to do my best. So maybe, hopefully, next time when I re-record it, I can address those mistakes and then improve my teachings, especially in this area, stochastic process modeling. So in the meantime, if you have any questions and suggestions, of course, then feel free to contact me. Okay. Again, I really would like to thank everybody for your time and effort for working on the IE 515 class. Okay. Thank you very much. Bye-bye.